It's loading. Okay. Hi, everyone. Thank you for joining our session today on optimizing high-efficiency heating systems for performance and savings. So today we have our experts, Steve and Michelle, who are going to be discussing this topic. And the next few slides, we're going to be going over some of Save On Energy's program enhancements, and that'll be done by Megan.
Thanks, Prasanth. Hi, everybody. We were expecting Vicky Gagnon today to give this update, but she is not available, so I'm going to step in. I won't have all the information, but we do have her contact info to share with you all too, in case you have questions about any of these program updates. So generally, the demand side management framework for 2025 through 2036, this is a 12-year funding commitment from the Ontario government of $10.9 billion. It started in January of 2025. Some of that funding does go to training and support, which brings you all of these webinars that we're delivering on a regular basis. This is a very different framework from what's been done in the past. Some notable new programs include the Home Renovation Savings Program, the expansion of the Peak Perks program, which is the residential demand response program. It's being expanded to small businesses as well, and the installation of solar PV systems for commercial customers. There's also going to be funding for local distribution companies to play a more active role on an opt-in basis. So there's three things we want you to take away from this morning. One, good news, there's more and many programs available to you. The challenge is to determine which one is best for your facility or your project. Two, there's detailed program information and support materials available on the Save On Energy website. And three, programs are delivered across the province of Ontario through Save On Energy's delivery partners. They have targets. You can call them. They all want to help you save energy. So we're going to focus on 4 programs this morning.
Sorry.
Yes, instant discounts. LED lighting is now offered through the instant discounts program. So you participate through distributors. There are over 400 distributors across the province. You purchase your lighting from them, provide the installation address at the checkout. They apply a discount at the point of sale. There's no paperwork required, no pre-approvals, no waiting for your incentive. Occupancy sensors are now included in the point of sale discounts, as well as network lighting controls. Network lighting controls are still available through the retrofit program. And some enhancements to the retrofit program. Effective at the end of this month. So if you're planning any projects, this will apply to you. New incentives are either the greater of $1,800 per kilowatt of demand savings or 20 cents per kilowatt hour of energy savings. Adders offer double the standard incentive for facilities in certain areas. You can find those areas on Save On Energy's website as well. And Energy Star certified computer servers, virtualization, and uninterruptible power supplies have been added. You can catch all of these news and updates on the website as well. And again, solar distributed energy resources, rooftop solar, is now available across Ontario to commercial customers. Micro generation for projects up to 10 kilowatts of DC power are eligible for $1,000. Small to medium generation projects between 10 kilowatts and up to a full megawatt are eligible for $860. And we also have the existing building commissioning program. If we go over to the next slide. There's a few stages to this program. Investigation, supported by a commissioning provider, also listed on Save On Energy's website. Incentives up to 6 cents per square foot of the facility, capped at 75%. The implementation phase, you implement some of the recommended measures. You get an incentive of 3 cents per kilowatt hour of savings. And the persistence phase, at the end of 12 months, you maintain those systems and get an additional 3 cents per kilowatt hour of confirmed savings at the end of the year. And finally, we have the Energy Performance Program, which is a holistic approach to energy savings, operational, behavioral, and capital projects. You get paid on the performance of your energy savings. Incentive is tiered at 15 cents per kilowatt hour on peak and 4 cents per kilowatt hour off peak. And that's it. We have some contact information. So these are the folks that want to help you. These slides will be posted also on Save on Energy training and support webpage on the Energy Efficiency in Buildings learning path. You can always find this information on each of the program web pages as well. Reach out. The teams are here to help you complete your projects as efficiently as possible. And lastly, just a thank you. Vicky's contact information is there as well. If you have any questions, she's always happy to help. Vicky Gagnon at iso.ca. And one last thing before I let everybody go onto our topic today, we have surveys that get issued by a third party called Forum Research. On the left is a screenshot of what an email looks like that you will receive. There's only 5 questions, very simple. We ask for your feedback so that we can continue improving the offerings through training and support. And with that, I'm going to pass it off to Stephen.
Thank you, Megan. I'll talk a little bit about the agenda here, what we're going to get into, and then I'm going to have Michelle kind of lead the way in terms of some of the systems and applications and so on. So welcome, everybody. Make sure if you have any questions, you can throw them in the chat. We'll actually do a poll in a couple minutes. So get ready to answer the question, what do you think about when you hear high efficiency heating systems? We'll go through the various different types of systems, their applications, but also their efficiencies as well. Michelle, you do a lot of work on recommissioning and commissioning. So commissioning these systems is very important. We'll have a look at some guidelines for that. I've seen, it was funny, I saw a condensing boiler system installed a few years back, and it couldn't even meet the load of the building because it wasn't commissioned properly. The combustion efficiency was just right out the window. So simple little things can make a big difference. We're certainly going to go beyond boilers today. So performance improvements with optimized controls. What can we do to really tweak those systems? How can we better control them to maintain optimal performance? And then finally, I'll come back and talk about building the business case for high efficiency heating systems. It's an interesting one. It's a tricky one. There are some good opportunities and some good tools out there. So we'll talk about those as well. So moving on. We're going to start out, really, what are our objectives here today is to understand the types of high efficiency heating systems. We're going to take the spectrum. We're going to start out with the least efficient to the most efficient, right? We're going to talk about the importance of efficient distribution systems, right? So for example, if we're going to a heat pump system, basically making sure we have a low temperature system of one form or another is very important. Otherwise, we're not going to be able to meet those loads. So it's not just about the heating equipment, it's about the whole system holistically. We'll give you some ideas about what to look for when proceeding with the design installation phases. Also, maintenance strategies, key things in terms of maintaining that operating efficiency, whether it be a boiler or whether it be heat pump of various different types. And then finally, sort of leave you with some understanding of what optimized controls can do in terms of thermostats, zone control, heat pumps, and things like that. And obviously the controls for heat pump systems are going to be quite a bit different than what you would use for a traditional boiler or other type of heating system. So moving on into the whole idea of system types and applications, we're going to do a little poll here. I want you to let me know what you think of first when you hear the term high efficiency heating system. So the poll isn't going to come up. You're going to put it in the chat. Let's see what people think about when they think about high efficiency heating systems. How far do you think we can go with efficiency? So let's have a look at what's coming in here. Type it in the chat there.
Ground source heat pumps.
Ground source heat pumps, right? Tight envelope, right? Low energy to operate. Absolutely. But I like IFRAM's one, right? There's no use in just having a high efficiency source. We have to have a system, meaning the building itself. ASHRAE guideline 36, right?
Yes.
So
Controls.
standards, right? Ground source heat pumps are coming up again, right? So when it comes down to it, and we'll see in the next couple of slides, Michelle will talk about the various efficiencies. Systems efficiency above 100%. Thank you, Juan. That's good. Hybrid system with fuel switching options, right? So how do we make the best of both worlds, kind of thing? So that's good. We'll talk a little bit about that too as well today. Is an electric resistance heating above? It's 100%. Absolutely, Andrew. I'm sure you know that.
It's
right?
in one of the slides.
Can we go beyond that? Well, maybe we can. Obviously, we can, because even though it's not technically more than 100% efficient, there is a term we use, or COP, which represents a system that appears to be more than 100% efficient. So, minimum exhaust temperatures, yes, for combustion equipment, right? If we want to make sure we minimize that flue gas temperature, that may require something like a condensing device, right? Which takes as much energy as possible out of that flue gas, or a flue gas heat exchanger.
And it could be also exhaust air temperature that you want to have as low as possible.
In the building, that's right. So we're not venting out valuable air. Ground source heat pumps, yeah. When it comes down to, that's right, Christian, when it comes down to it, I mean, you look at the source device, probably one of the most efficient ones is the ground source heat pump, but there's a lot of other factors to consider. All right, so let's move along there a little bit. And Michelle, I'll let you run with this one for a while. So we're going to talk about efficiencies, but I thought it was important to understand, what do we mean by efficiency?
Yes, exactly. And usually when we talk about heating equipment efficiency, we talk about what we see at the top of this slide, nameplate efficiency. And nameplate efficiency, for me, is just benchmarking. You select based, let's say, on nameplate efficiency. It is often unrelated or very remotely related to your actual in the field efficiency. So what you have thermal efficiency for most combustion equipment that you will see on the nameplate. For heat pumps and air conditioner, you'll see COP for heat pumps, usually EER for air conditioner. For larger equipment, you'll see kilowatt per ton sometimes. But you got to be very careful. We're going to talk about that. Those, like I said, they're really nameplate. They're laboratory tests. And they give you the efficiency that should be there in a steady state equipment. You also have on some equipment annual efficiency. You still have to be very careful about the annual efficiency because they're still rated in labs under specific part load. The more common one is for small residential size or very light commercial size equipment, such as the AFUE, which is the annual fuel usage efficiency that you'll see for furnace and boilers. That gives you an idea over a year how it is. The SEER, which is for air conditioner, again, usually fairly small size, and HSPF, which is for heat pumps. They give you a better idea of your annual efficiency, but it's still not your field installed efficiency. The last two are more for commercial size equipment. IPLV is for usually chillers. You can also have it for large heat pumps. Again, gives you an idea of what it is at part load. So if you had to go with one of the two, you're better off comparing your equipment when you purchase the equipment based on the annual efficiency. Again, highlighting that it may not be your annual efficiency, which will be impacted by way more other operating parameters than what they do in lab. And when you have thermal equipment efficiencies, because in high efficiency heating system, we don't necessarily discard combustion equipment. But you have to be, again, careful the distinction between combustion efficiency, which is what is tested in most buildings on an annual basis. That just tells you how well you burn the fuel. Doesn't really tell you much about how well it's transferred to your medium, which is usually air or water or glycol. That will be thermal efficiency. So your combustion efficiency is always high compared to thermal efficiency and very high compared to seasonal efficiency. Seasonal efficiency will take into account all of the operating parameters, such as the shutting off and on of a boiler, the losses from your loops, and all that. That usually can drop your efficiency, sometimes by as much as 20 or 30% of absolute point in efficiency. So always be careful when we talk about efficiency. it's not just about the number. In the end, it's really about how you use it. You can have the best performing equipment that will have a terrible annual efficiency, and I include ground source heat pump in that. Ground source heat pump are probably the best in terms of efficiency. Stephen, we said it's COP, so it's a kind of a, we're stretching the language here by calling it efficiency. But if your backup is always on, or if your wells have not been well balanced, and if your thermal load is not well balanced, that efficiency can drop below that of a good air source heat pump. So always be careful. It's a question of not just how you select, but how you design and how you use it. Typical range of efficiencies. Atmospheric combustion equipment, hopefully you'll get rid of all of that in the short, medium term.
That's my favorite one, because on the nameplate it says 80%. All the nameplates say 80%. Well, you'll never get 80%.
Yes. And obviously you get condensing combustion equipment, you get to the hopefully above 90%. If you're below, actually, technically, if you're below 88%, you're not even condensing. So at 85%, you're not condensing or very little. Electric boilers, it says 98 to 100%. The 98, the reason why it doesn't say 100% is because they consider let's say the jacket loss from an electric boiler, because the boiler itself is 100% efficient. Any electric equipment other than a heat pump is 100% efficient. So if you see ads on TV selling you a box that has infrared lamps to heat your space, it's not more than 100%. It's 100% efficient. And then you get to the air source heat pumps, which can nowadays be very efficient. Not as efficient as a ground source heat pump because it's dependent on the air, which can get really cold, therefore reducing your COPs. But you can have a good air source heat pump that will have an annual efficiency above 250%. 350 on an annual basis on air source would be really, really good. Maybe for the small cold climate heat pumps, even we can maybe achieve that. But for most commercial size air source heat pump, you will probably not achieve that. And there's variable flow. We'll talk about variable refrigerant flow system, which is basically another type of heat pump. And obviously the water or ground source heat pump, because the ground source heat pump is really a water source heat pump. And they can be, typically, the rule of thumb I have for heating in most Canadian location for a ground source heat pump is 400% on an annual basis. That's what I see most commonly.
So Michelle,
yes.
it was condensing boiler. What could be the minimum return water temperature? The condensing boiler's efficiency very much depends on the return water temperature, and if you're above 130, right, we're probably not going to be in condensing mode. So that's kind of the threshold.
And we have a slide on that, but you're absolutely right. There's a magic number for condensing boiler. 130 is a good. It's a good rule. Technically, if you have the right amount of outside air, 10% excess air, it's 133, but very, very, very few boilers run at 10% excess air, and we'll get back to that. So atmospheric equipment, that's your baseline. This is not a high efficiency system. It's in this presentation just to present you what is the worst case scenario that you can have would be the atmospheric combustion, which means you don't control what we call the excess air. It's really established by the equipment. Very often the boilers, the atmospheric boilers, you have no control of the amount of air compared to the amount of natural gas that's being burned. So what we call the excess air is really high very often. Plus the flue losses can be quite high too, because very often the flues open at all times. So it's the least efficient on an annual basis of all the equipment we're presenting here. There's still quite a few around. And I include in that the hot water heaters that you'll find in a lot of commercial buildings that are just atmospheric hot water heaters that have an annual efficiency around 55%. So even if the nameplate would show, even though they don't show nameplate on most hot water heater of 80%, it's not. It's about 55%. But you'll see those all over the place. The applications are very standard, air-based distribution system, such as rooftop units, and a lot of hydronic systems. Now, we're going to move up in the scale of efficiency. You can obviously go to power combustion equipment, but with legislation now, we're all going to go to power combustion equipment that will be condensing. But before we go to condensing, let's talk about the near condensing power combustion equipment. The benefit of those equipment compared to the previous one is that you have a blower that will actually mix the amount of air. It has a valve, an air valve and a gas valve. You'll have the proper amount of air going into your combustion of natural gas. Actually, hopefully you'll have the proper amount of air. If you have too much, you have too much excess air and your performance will drop. But those equipment, instead of being maybe 65% annual efficiency, they can be 75 to 80% annual efficiency if it's not cycling too much. So you've already stepped up considerably compared to what we just saw. But again, the applications are very standard. You can have exactly the same application as the other one. That's why it's an easy step up. But you will unlikely take that step nowadays, because the next equipment that you will have is the one we talked. It is the most efficient combustion equipment you can have, which is anything that's condensing. Nowadays, you can buy almost any kind of equipment that's combustion based and that's condensing. You have boilers, you got furnaces, you can buy rooftop units, makeup air units, and domestic hot water heaters that are condensing. But like somebody asked in the chat, you need to have a cold return. The little graph that's right here, I'm going to zoom in for a second here, tells you the story. You can have a condensing boiler that is not condensing if your return is above here it says 140, but really you have to be below 133 to be precise. But that's when you have 10% excess air. But you're unlikely going to have 10% excess air. You're probably going to be at like 30, 40, and 50% excess air, which means your temperature of your return needs to be lower and lower. The more excess air you have, the lower your return needs to be to achieve condensation, because you need to reach what's called the dew point of your flue gas. So in that green zone, you get condensation, and here it says fuel saving, but obviously you're efficient. But always check, a condensing boiler is not condensing by nature. It's condensing when you run it in condensing condition. And if you install a condensing boiler in an old building that has really old rads and all of the perimeter heat needs to be at 180, well, you will have a high efficiency non-condensing boiler even though you bought a condensing boiler, because even though you may want to return lower than 130, your building won't allow you to return below 130. Otherwise, you're not going to meet the load. So that's something you always need to keep in mind. And we'll get back to what you can do about this, because you won't change your building right away, even though somebody did properly mention that reinsulation should be considered. And that's one of the reasons, because if you have a really poor building, your condensing boiler will not provide you all of the savings, because the heat load requires a high temperature loop. Otherwise, you need to change all your radiation loop to low temperature, which is really, really expensive. But keep that in mind. Condensing equipment needs low return. Stephen, there are boilers that are made to have two return, a hot return and a cold return. And for those boilers, you can actually return a loop that's a little hotter. Let's say at 140, 145 return. That would be at the bottom, and then at the top you've got another return, and you can return then your makeup air unit, your air handling unit return, and that will be a cooler return, and it will allow condensation. So if you have two separate loop, and you can buy a boiler that has those two return, you can then get condensation as long as you don't mix the two return prior to going to the boiler. So that's something to keep in mind. You can play around with the configuration of your loop to make sure you get as cold a return as possible, or get a model of boiler that will allow you to return different return temperature at different location in your boiler heat exchanger. So that would be the better type of combustion equipment, and you can achieve really high reduction in greenhouse gas emission with that, but obviously you still burn natural gas. The next step would be to go to electric heat. And I told you, somebody mentioned that electric heat, regardless of what you hear, it's always 100% efficient because whatever electricity goes in comes out as heat. Now, you may have some losses from distribution and from the boiler, and people will say, well, it's really 98% efficient. That's about the system efficiency, not the boiler efficiency or the baseboard efficiency. If sometimes I do audits, Stephen, and an operator will say, oh, my building, it's not really efficient because it's got electric baseboard. And I don't blame them. What they mean is it is not cost efficient. It is very energy efficient, but it is not cost efficient because, as this slide shows, and everybody knows, when you have electric heaters, very convenient because you can install them in a lot of different zones, easy to install typically, but it can really catch up to you with the peak demand cost and the electricity cost in general. If you're a Class B customer in Ontario and you pay your electricity energy at 12 cents, that's going to be expensive to run, obviously. The ideal configuration, and I see that a lot around my ways, I'm in Quebec City, is to have a hybrid system. And there are some buildings in Toronto that used to have that, and now they're being recommissioned where you had electric boilers and gas boilers. And as long as you're below peak demand of your building, and let's say you're a Class A customer, I don't want to get too much into the details of that, Stephen, but you can run that electric boiler at a cost that is below that of a gas-fired boiler, as long as you stay off peak. So that hybrid idea, which somebody mentioned in the survey we did at first, is actually one of the better type of configuration you can have, especially if your hybrid is not with an electric boiler, but with any type of heat pump, ground source heat pump, air source heat pump, and we'll talk about that. Those hybrid system becomes really, really a good solution. Now, if you want to go electric and you don't want to buy a heat pump for XY reason, you can always manage your demand with thermal storage. Again, those are getting quite common. Actually, around my way, they've been common for quite a while, but I know I've seen a few in Ontario where you have basically a pile of brick that are heated to like 2000 degrees Fahrenheit at night during off-peak hours, and you discharge them in the daytime, just like you do with those ice bank that you have for air conditioning. And you can have them both for air-based system or hydronic system. It's basically just a pile of brick, going back to really old principle of how do you store heat, put big rocks in the fireplace, and that's basically what this is. But it is per se 100% efficient, but there are losses. So as long as those losses are reused, because at 2000 degrees, even well insulated, you get a lot of losses, about 2 or 3 kilowatt of losses. So you need to be able to reuse that to have, I'd say, 100% efficiency out of your electric storage system.
Yeah, a lot of people get confused about that because any loss from a heating device, either hot water or space heating device within the building, is still within the building envelope. Now, a hot water heater, if you losses in the summer, obviously that doesn't contribute to heating. But to a large extent, even those standby losses from many of those systems are actually contributing to space heat. So it's not that inefficient in that sense.
Exactly. As long as you reuse it. And we'll talk about a heat pump water heater, because now we're in the heat pump section. Now we're in the true high efficiency systems, even though the one before, condensing boilers, electric heater, they're highly efficient. These are more than what we said, 100%. It's not really 100% efficiency, it's coefficient of performance, because the heat pump, as the little graph shows here, it takes heat from outside and boosts its temperature so that it can be useful inside. So it's a heat mover, basically. It moves the heat up the hill from a low temperature to a high temperature. And the least difference there is between that hill, the evaporator and the condenser, the more efficient your system will be. So the reason a ground source heat pump is so efficient, there's no magic into it. It's not because the ground will give you, magic heat. It's because it reduces that lift between the evaporating temperature and the condensing temperature, because the ground never goes to minus 20 degrees like the air will do for an air source heat pump. So an air source heat pump, you'll have them, and it's been around for so long. I mean, Stephen, your dad had an air source heat pump in the 70s.
1973. Yep.
Yeah. So And you can have that for hydronic, mini split, rooftop units, water heaters. The one thing about those application of heat pumps, it's not just the size of the heat pump that matters, it's the temperature. And that's why at the top here it says small to large commercial with low temperature hydronic. As most of you probably know, most heat pumps will not be very efficient if you pass the about, and I'm sorry it's going to be in Fahrenheit, about 140 Fahrenheit of supply temperature for hydronic loop. You would have to go to a cascade system, which means 2 heat pumps in series, and your COP really drops, your efficiency really drops. So always look at your building and say, okay, I want to use heat pumps, but I need 180 all the time because my building envelope is so bad. And to go back, I think it's Afran that mentioned reinstallation. The heat pump may require you to have less losses from your building because it will not provide you the 180 degrees. You're pushing the envelope very often at 140 because the COP is already dropping. Most of the time, to have the optimal size of heat pump, you don't design a heat pump for 100% of the load. Very rarely. You can. I'm not saying you should not, but on an economic basis, it's usually way better to design it to about 70% of the peak load, maybe 80%, it varies, and have the 20% capacity being another source, which is usually natural gas. You'll meet 90% and more sometimes of your actual heating demand with your heat pump, because that supplemental heat is only there for those coldest days where you actually need 180 or you need above 140, and you need that supplemental gas heating. Sometimes it's electric, straight electric, but demand will be very painful to pay if you've got an electric backup to a heat pump system in most jurisdictions.
It's actually a lot better than a hybrid vehicle. Hybrid vehicle, you don't see as much of the combustion engine reduction. With a hybrid heating system like this, as you say, Michelle, you can eliminate 90% of your fuel consumed, right? Yeah. For maybe 50% of the capacity. So it does make a big difference.
Now, when you talk about smaller equipment, such as mini split in terms of being efficient at low temperature are way better than the larger system. You can get what's called cold climate heat pumps, which includes a lot of mini split that can run with a COP of 200% or an efficiency of 200% all the way to -25 to -30, with sufficient capacity often to meet the load, not of a whole building, but of a small space within the building with no backup. So mini split in terms of efficiency at low temperature, in terms of air source heat pumps, are by far right now the best available system where you can get away without supplemental heat. Rooftop units, they've been available with heat pumps, but again, you've got the hybrid rooftop units. It's probably the only way to be able to meet the load without oversizing the unit significantly, which would reduce your efficiency also significantly. Heat pumps do not like being oversized. They will cycle on and off. They will lose a lot of their efficiency. So right-sizing heat pumps, and we have a slide on that, is important. So if you don't want to oversize because you know your capacity is going to drop with outside air temperature, you again go with a hybrid system, which is usually heat pumps and natural gas. There are ways to control that better than just based on outside temperature, and we'll probably talk about that if I don't take too much time here, Stephen. Water heaters, quick word on that. Always install them in mechanical rooms that have a lot of heat rejection. We talked about the heat rejection being reused for useful purposes so that you don't lose that 100% efficiency. A water heater is heat pump is an air conditioner, unless it's a split system, which are pretty rare right now. So it's a single block system and it's in your mechanical room. It actually cools the mechanical room, captures that heat to heat the water. So that's an easy measure to install in most commercial building, unless you have those little electric heater distributed in all the washroom, in which case it becomes quite difficult. A lot of retrofit can be done with VRF system, variable refrigerant flow, which basically can be the same as a heat pump. There's two configurations, a two-pipe system, a three-pipe system. A two-pipe system is basically a heat pump with multiple interior units, which we usually call heads. You've got multiple heads. The entire system is either in heating or cooling. So if one unit wants heating, all the units going to get in the heating mode. A three-pipe system will recover the heat from internal zone to perimeter zone because they can be in different mode. You still have only one unit outside with multiple heads inside, and you've got this third refrigerant duct that's kind of a neutral one that allows you, I'm not going to go in details, to recover the heat. The one thing about the efficiency, this is a really high efficient system, but the longer your refrigerant piping runs, the lower is your efficiency. They will provide you the efficiency with the nominal length of refrigerant piping. If you go past that, you will have a significant drop because basically you're pumping that refrigerant using the compressor. The longer you do, the more your COP will drop. And again, there's a lot of refrigerant in there, and I'm not going to go into details of that, but if you select that system, consider also the amount of refrigerant that will be in your building once you have that system in place.
And they do require highly skilled technical staff to install and operate properly.
And if you select it, make sure you select a unit that is BACnet compatible. A lot of units were impossible to integrate a few years back into a BAS system. Nowadays, most units will be able to be integrated. So make sure it is a BACnet compliant system. And it can be applied to large buildings. I've seen very large office buildings that have multiple loops. You do have to break it in multiple loops to avoid having too many heads on a system. There's limits. It allows you for individual control. In terms of what you can do in terms of optimal control, your handcuff. There's very little you can do other than control set point. Those systems are packaged. In terms of their internal controls, you're really kind of locked out. It's really just about set point control that you can do anything about. The other type of heat pumps that you should be considering, and again, very old solution, water loop heat pumps, very efficient. They're very similar to a VRF, except they have a hydronic loop linking many different water source heat pump. The one measure that can be done on existing system is usually those systems have a boiler. When the loop gets too cold in the winter, you need to inject heat in the loop. And people inject heat with a boiler, but that's a low temperature loop. It's usually at about 70 degrees Fahrenheit in the winter. It's a perfect application for either a ground source heat pump or an air source heat pump. You remove that boiler, or you actually use a boiler just as supplemental, and you put an air source heat pump in there. You just decarbonize your loop by probably 80 to 90% because it's a low temperature loop, perfectly suited for air source or obviously ground source heat pump, but ground source heat pump is way more expensive than air source heat pump. Heat recovery chillers, you've got two types. You've got one with an auxiliary heat exchanger, that's usually a plate exchanger in series with a condenser. They are less efficient in producing high temperature water. So a double bundle will provide you, double bundle means two condenser. You got a small condenser bundle for the winter that will be able to provide you that 130, 125, depending how you select it, all the way to 140. That's an old solution being rediscovered in a lot of building. And obviously you've got geothermal. Geothermal, the most efficient. There are drawbacks to that, mostly the cost. You got to pay for those wells. You got to have about 150 feet of well per ton of refrigeration. So it can be expensive. Your load has to be well balanced. If you have a lot of heating and not a lot of cooling, you can actually freeze your borehole and reduce your efficiency significantly. So you try to balance your load, or you have to size your well properly for the design heat load. Otherwise, you will have, actually, you can get a big degradation of your efficiency with time if that is not well balanced. So obviously, water source heat pumps, usually if they're in existing building, the best thing to do is to check if you can replace the boiler or supplement the boiler with an air source heat pump. But they can be applied to large commercial institutional building. Same for heat recovery chillers. And if you really want to achieve higher temperatures because you want to get rid of the boilers, you will need to go a cascade system, which will take the condenser heat, use a high temperature heat pump to boost it from, let's say, 120 to 160 or 170. And ground source heat pump, we talked about ground source heat pump. I just gave you a little bit of warning about what to make sure the wells are well balanced, they are well sized, and the hybrid system. Very quickly, when you have a hybrid system, try to control based on building peak demand. Same if it's a rooftop unit. Just based on temperature is okay, but it's not optimal. Always try to say when my system, my electric system, which can be a heat pump or electric heater, is going to exceed a certain peak and create a new building peak, switch to your supplemental. And that will minimize the cost of using the heat pump. Sometimes will result in saving depending on your rate. So that's how most hybrid systems, and there's tons around here, they're almost all controlled based on peak building demand rather than outside temperature. Just the simplest system are based on outside temperature. Stephen?
Well, what actions have you taken or believe you should take prior to installing a piece of high-efficient heating equipment? So we're going to talk about some of those pre-installation and commissioning guidelines. But basically, what have you done? If you've done this, maybe nobody out there has done it. I'm sure a lot of people have done it. So what actions have you taken or do you believe you should take prior to installing high-efficiency equipment? My favorite one is, somebody already mentioned my favorite.
Yeah, I was going to say, somebody said, reduce the load.
Reduce the load. Absolutely, right? You know, don't make these systems work harder than they need to, right? And because, you know, it's always going to be more cost effective, almost always, to reduce that load, especially through waste and operational efficiency improvements. So
very quickly, a few pre-installation consideration. Temperature levels. I know I'm not going to follow the slide. You'll have the slide. When you pre-install, make sure that you have the proper temperature levels that are optimal for your system. Your high efficient system will usually, almost regardless of the type, condensing boilers, heat pumps, they are very sensitive in terms of performance to the temperature level. So try to make sure this is well addressed in your design consideration. Electrical capacity. It's very nice to say I'm going to install a heat pump, but you need the capacity, and you need that capacity at the right location. So it's all about, you know, making sure that if you need a new electrical feed, that can, you know, balloon the cost of your project. So be very careful about that. Commissioning, the higher the efficiency of a system, the more the performance can degrade with poor commissioning. And we see that in LEED buildings all the time. Very complex buildings that are supposed to be highly performant will have poor performance because of poor commissioning. Not necessarily because of poor equipment or poor selection, but very often poor commissioning. So we're talking about commissioning. When you have a high performance system, again, it's critical that you start your commissioning process from the design so that, yes, the equipment has been selected for the right temperature. Your backup system is selected and is supposed to be controlled based on peak demand or on temperature. All of that has to be examined before construction starts. And when construction starts, you have to be even more careful about how the piping is. We saw, Stephen, an example of a boiler with those two inlet and the pipe, they mixed.
Never connected.
They mixed the return prior to going to the two inlet. So verify during construction. It is way more critical than a standard system. And during the acceptance phase, you need to check the performance of the system. So you have to verify the on-site COP. You have to verify that if you've got ground source heat pumps, that the well is well balanced. And the commissioning agent should not be the installer. It should be a independent third party, and they will check and they will have a deficiency list and say, hey, why is the performance instead of a COP, a nominal COP of 6, why do we get a COP of 4? Until those are resolved, you're still in the warranty period and final payments not made. But high efficiency systems are more expensive. So going through the requirements, and I'm just going to go through that because you're going to have the slide, but basically make sure It starts from the design. The design is reviewed to meet your objective. What you want to achieve with that system? What are the loop temperature? What is your requirement in terms of peak demand if you have a hybrid system? And all those checks to be done during construction. Like I said, significantly more important. It's important in standard construction, but for high efficiency systems, you can go from a condensing boiler to almost atmospheric boiler efficiency if you don't do it properly.
Yeah, I saw one of the internal loop heat pump systems where they were not understood. It was not understood, and they actually running the boiler and basically to heat the loop and actually turning off the heat pumps. It was crazy, right? So
Yeah.
if people don't understand the intent of that system,
and I saw condensing boilers many times installed with fully modulating burners with 1:15 turn down ratio being used on off, poor commissioning.
Yeah.
And then those on-off cycle lose 15% of absolute efficiency point on your condensing boiler. The other thing before I give it back to you, Stephen, is about control sequences. How many times do we see systems being installed, especially condensing boilers, and the controls have not been changed? You need to review your control sequences. Condensing boilers are usually more efficient, almost always more efficient when they run as much as possible in parallel. They need to have a cold return, so your reset schedule has to be changed. Your control sequence has to be changed. When you run with heat pumps, same thing. It's not just about the control of the heat pump. You have to look at your reset schedule for your air handling unit, because let's say you have an air handling unit that is requiring is requiring air at 10 degrees Fahrenheit for some reason. The colder you demand, the higher is the step that we showed you between condensing and evaporating, the more you lose in performance. Same for heating. So you have to review your reset schedule, not just for the hydronic loop, but also on the air side system, because all of those systems, heat pump, condensing boilers, they like it cool. Therefore, you have to review your reset. Obviously, you have limitation based on your heat loss of your building, but if you just leave everything as it was prior to installing the heat pumps or the high efficiency boiler, you're almost guaranteed to leave savings on the table, because you will force the equipment to run in inefficient condition. So I just summarize here. You have to change for boilers, you have to change your reset schedule, change your lead lag or your sequencing if it's lead lag. For heat pumps, you have to review all of the supply temperature to make sure that you supply as low as possible. If you do setback always saves energy, including with heat pumps, unless you don't do a proper optimal restart. Heat pumps are very tight in capacity, so they can take a long time to warm up a building, and very often the control system can kick in the supplemental heat to try to catch up, and obviously that will defeat some of the savings from the setback. So you can do setback, but you have to make sure that you tune properly your optimal start. Otherwise, you may actually start losing some of the savings you had. So sorry about running through that, but we're a bit tight on time. You'll have the slide, and we'll go to Stephen for a business case for those high efficiency systems.
A lot of good content there, Michel. Thank you for that. So, yeah, I mean, most of you have probably looked at this. What financial barriers or maybe opportunities have you encountered when attempting to or implementing a high efficiency heating system? You know, why can't you do this? You know, why you came up, you had an energy audit, you presented the business case, and somebody said nope. Why? What are the challenges here? Let's see if anybody throws anything into the chat. Hopefully I can still see the chat here. Thanks, Megan.
Or maybe keep an eye on the chat, and I'll let you know if anybody chimes in.
I always like to start with this. I used this slide, I don't know, probably 30 years ago the first time. But basically, I think we have to do to really understand the basis of the financial case is to understand what is the relative cost of the delivered energies, right? So if you have a natural gas device operating at 85% efficiency, right, and you're buying natural gas at 40 cents a cubic meter, which is equivalent to 33.8 cents per equivalent kilowatt hour, you're delivering heat to the space at about 4.5 cents an equivalent kilowatt hour. So that's what the heat is worth delivered. Now you take an electric heater. Now this is all excluding demand, and Michelle is right to point out that demand can make or break these things. But without demand, if you can avoid the demand, if you can run your system in a way that you don't impact that demand, then at 14 cent a kilowatt hour electricity, that's like an electric heater. That's like delivering heat at 14 cents a kilowatt hour. So we can see why in the past many people have gone from electricity to natural gas. Now we got to make the transition back potentially overall. So in an air source heat pump with a COP of 2, you can deliver heat at 7 cents an equivalent kilowatt hour. With a ground source heat pump, say we're pushing up to 350% or a COP of 3.5, now you're down to 4 cents equivalent kilowatt hour. So now you're beating the natural gas. And in fact, to your point, Michelle, earlier about a heat pump on Class A using an air source heat pump where you basically your global adjustment is paid on your 5 top peaks previously. You don't hit those peaks and you don't hit the local distribution peaks themselves, the demand charge. So you're paying 5 cents, maybe even less than that per kilowatt hour, depending on the rate that prevails in your region. You're looking at 2.5 cents an equivalent kilowatt hour. So right off the top, you can see, what you're up against here in order to make one of these things pay. The problem is that in some cases, I'm going to say the challenge is simple payback isn't going to be good enough for evaluating these systems. So you needed a better tool to do that. Now, the other side of it is the carbon associated. So this one gets even better because natural gas, 210 grams per equivalent kilowatt hour of heat delivered, whereas with that ground source heat pump, it's 0.01 kilograms per kilowatt hour. So if you're going to build a business case, I think it's clear you have to think about both the financial and the carbon piece, right? And if you give preference to carbon, how are we going to monetize that in our business case, right? Now, obviously, the landscape for that is changing, and it'll probably change in the future in terms of what the sort of the price of carbon, the impact of the price of carbon is. Number of people throwing things in here. Electrical service. I'm going through that right now with a church building that I voluntarily manage, trying to squeeze in a heat pump or two, given an older service entrance, right? Funding, obviously. Electric feeders or constraints. Operator buy-in, absolutely, right? Yeah, Supri, I mean, there are a lot of times that this new equipment isn't necessarily understood or accepted from an operational standpoint. So we really have to work to get that engagement and to get the buy-in from the operator side. Right?
I just had an experience with somebody that was arguing with me that heat pumps are less efficient than electric baseboards. And I could not change that operator's mind. For some reason, convinced that heat pumps are a bad thing. So there is a training aspect to this high efficiency equipment.
Yeah, like I said, I mean, my dad had a heat pump in his house, 1973. I don't know how many, that's over 40 years ago, right? 50 years ago. I'm getting pretty old, don't understand that anymore. Okay, so, I mean, that's the basics, right? We're going to get some carbon impact, which is very positive. We're going to have potentially some positive financial impact, maybe some negative, depending on which we pick. How are we going to evaluate this? Well, I'm not going to give you an answer today. I'm going to say you need to use some kind of tool to do that. I would use RedScreen Expert to make my evaluation. It has some great tools. If we're simply looking at going to a condensing boiler, right, improving its efficiency, the efficiency models of RedScreen work really well. But if we're, say, looking at and when we do this, we actually get out of it not just sort of the technical evaluation. On the next slide, Michelle, we get a nice financial case, right, where we can show something like simple payback, and we go even deeper and calculate net present value, internal rate of return, all those good things to build that financial case properly. All the tools are there. If you're interested, I even have a very basic spreadsheet you can use. In fact, Megan, we're going to be doing some stuff on this, through Save On Energy in terms of life cycle costing and heat pumps, right? Not necessarily a webinar, but there are some tools. My son Adam has done some webinars on that using the life cycle costing tools for things like heat pumps on the Save On Energy's website. I think, Megan, you can highlight that later. So there's lots of resources out there. Simple payback may not be the best way to evaluate them. And then finally, the carbon impact, right? So using these tools, we can definitely see that carbon impact. In fact, if we're looking at, say, a rooftop unit, I'm doing this quite frequently, actually. On the next slide, we see, obviously, a rooftop unit being installed. Building the case for that and maybe doing it as a hybrid system. RedScreen has a great tool for that. It's called the the power heating cooling model, and it actually allows you to sort of do some basic sizing calculations and look at that, what I call the 50-10 rule, where you can 50% of the size get you, 90% or 10% remaining carbon. Red Screen's tools are set up really, really nicely to do that, and we're going to have some.
Stephen, a lot of people were saying that the electric feed is a constraint, but if you use a tool like that, you can see how much. Maybe sometimes you can install a relatively small new system that's electrically based, like a heat pump, and still get a large share of the heat. And that tool would give you some idea of how much you can achieve with a reduced capacity system.
Yeah, and as you said, heat pumps don't like to be oversized.
No,
so
they don't.
If you marginally size or undersize it, then you've got to control it properly, but you get the optimal efficiency out of them running that way. So just to summarize the section, right? The business case for electrification, which is really what we're talking about here. It could, on a 20-year time horizon, it could have a positive net present value or be neutral, or in the worst case, it may not pay, right? But basically, every situation has to be taken as it is. It's very difficult for me. If I were to give you an answer here, that if you're going to do this, you'd get that, I would likely be wrong. So what I'm going to encourage you to do is do the math on this one. But obviously there's lots of consultants out there that can do this, but also take a look at some basic tools that are out there on the web for doing sort of basic financial evaluation. Build your business case that way. And always, all of these things are long-term propositions. So again, simple payback doesn't work. What you've got to do is you've got to look at this over typically a 10, 15, or 20-year time horizon. Do the evaluation that way. Do the present value analysis, right? Determine the lowest life cycle cost. And in that situation, you'll probably get the answer that favors electrification. But it's not just simply a matter of simple payback. All right. I think that's the end of our section, right? Oh, business case enhancement, looking at all the other pieces, right? So the carbon pieces, but all the other benefits, right? And we heard this morning, I was doing a webinar with BOMA, and we heard this morning from one of the property management companies why they're doing certain things in their building is because their tenants are asking for it, right? So making sure that, if you've got customers, the customers are aware of what your intentions are, because that can become a big part of the business case for doing this, making your building far more attractive. And in the long run, increasing the building's value, absolutely, through A, it's got current technology, but B, right, obviously lower operating costs if that case can be made. So, and there are some really good incentives. Go ahead, Megan.
Thank you. So we don't really have a ton of time for question and answers, but I'm going to put our email in the chat here. And you can always email us with questions, and we can either direct them to Stephen or Michelle or answer them directly as well. You can also visit our webpage. This is one, there are 5 learning paths on the website. This one I'm copying in the chat right now. Actually, if you scroll 75% of the way down the page, you'll find the life cycle costing tool there that Stephen was talking about. But there's plenty of resources on this website about electrification, about energy efficiency in general. So we encourage you to have a look. As a reminder, again, please do take 5 minutes to fill out our feedback survey when you receive it in your email in a couple of days. And this presentation will also be posted along with the recording on the Save on Energy website. Sometimes it takes up to 2 weeks for that part.
And Megan, the other thing is just mentioned is the coaching, right? Because folks have opportunity to have coaching. If you want Michelle to have a look at some ideas you have and critique them or add to them, we can definitely do that. So that's supported by Save on Energy. So reach out to the team here, and they can direct your question or request for coaching to either Michelle or I or both of us. So one way or the other, we can help you out.
Thank you so much for that reminder. We have, anytime you come to one of our events, if you want some one-to-one coaching afterwards, we'll find the right expert to pair you up with and look at your particular situation one-on-one.
Thank you, Megan.
Thanks, Megan.
Everybody.
Thanks, everybody.
Everyone.
Thanks for the kind words in the chat there.